Okay, so today's topic is thermochemistry, and thermochemistry is the study of the changes in heat in a chemical reaction. And what's important is that we've been studying chemical reactions without really even looking at what's going on, other than looking at what reactants are involved and what products are involved. But inevitably, there's either going to be a heat loss or a heat gain. So there's always a thermo component of every reaction that takes place. So let's first then talk about the concept of heat. And understand that heat is a very specific term, and it's the energy that's transferred from one object to another because of differences in temperature. So for example, if we take this situation where we have let's say this is a block of ice that's at 0 degrees C, and then we have someone's creepy hand, and that's at 30 degrees C. You can understand, obviously, that we have two objects that are different temperatures, and in fact, we're going to have the flow of the energy moving in one very specific direction. When this hand comes up and touches that block of ice, the heat energy is going to move from the warmer thing to the cooler thing, so from the hand to the block of ice. Okay? And again, what's important for us to understand here is that everything is going to have a slight difference in temperature. Even things that are at room temperature together are going to have, for moments, slight differences in temperature. So there's always going to be this flux or this movement of energy that takes place as a result of the difference in the temperature of two objects. Okay. Oh, I suppose there's something else I should talk about while I'm here, which is this concept of temperature. The one thing that I want to make sure is reinforced with you folks is that heat and temperature are not the same thing, right? Temperature is the way that we measure the heat energy of an object. And so we have differences in temperature because we measured it with, say, a thermometer or some sort of scanner, so that we can understand that difference in a measurable way. Okay, here's the next thing I want to make sure we understand, and it's something I mentioned just moments ago. All chemical reactions involve heat. Now, this heat actually could either be a release or a consumption of that heat energy. And in fact, if it's a release of heat energy, then we refer to that whole reaction as being an exothermic. Exo means out, thermic means energy, so we have out energy or release of energy, and then we have the exact opposite, which is an endothermic reaction, and endo means into, thermic energy again, heat energy, so we have energy going into the chemical reaction. Now, let's take a look at this in terms of what's actually going on. Where's that heat coming from, or where is it going into? Well, you should know it's all about bond energy. We've talked about bonds before, covalent bonds, ionic bonds, and we've even maybe talked a little bit, very briefly, about intermolecular bonds, hydrogen bonding, dipole-dipole, dispersion forces. We'll learn more about that later. Okay, don't forget these are intramolecular that I've bracketed here. So it's the bond energy. When you release, when you take energy, it takes energy to break bonds. That's an important thing to understand there. So if you want to break a bond, it's going to require energy. And you release energy if you make bonds. Now, it's all about sort of a net gain or loss of bond breaking and bond making that determines whether something is an exothermic or an endothermic reaction. So let's shift down here a little. I don't have enough room. Let's go to another page here. And start up in this corner. So imagine a situation like this. I have a beaker, and there's some sort of chemical reaction going on in my beaker here. And if we had a theoretical zero-sum situation, which you're not going to have, keep in mind that that's not possible in a reaction to have a perfect no energy release and no energy consumption. But imagine this in theory so that I can explain to you what's happening in reality. In theory, imagine that we have a down arrow that's black. Okay, so this black down arrow is bond breaking. Because like I said earlier, it takes energy to break a bond, so I'm putting energy in to this beaker. All right? So that's energy going in, bond breaking. But then we have bond making, the up arrow. And as I just said moments ago, bond making releases energy. So that's why I have the energy going out. So you can think of these vectors as not only being explaining it's either breaking or making, but also think of it as being the amount of energy. So we have energy going in for bond breaking, energy coming out for bond making. And if we have those vectors are the exact same size, same length, the inputs and the outputs are the same, then you're going to have no change in the energy of this system. There's not going to be a release of energy, there's not going to be a consumption of energy. Again, that doesn't actually happen because something's either going to be exothermic or endothermic. So let's take a look at an exothermic situation. Remember, this is where energy is released here to the outside. And in this case, this is a reaction that releases heat to its surroundings. And so, in fact, exothermic reactions, they feel hot to the touch. Okay? Heat is released because the energy used for bond breaking, remember that's what you have to goes in, is less than the energy that's released for bond making. So it gives off energy as a result of the reaction. Let's show this again with what I was just creating with these cute little beakers that I have going on here. Okay, here's my beaker. So in this case, my bond breaking is going to be a tiny little arrow because that's the amount of energy that's required to go into breaking up the bonds, whereas my bond making is going to be a much larger arrow. Right? So this difference that exists here, that I'm just going to create right there, that difference is the amount of energy that's released to the surroundings. Okay, so what are some examples of that? Well, we actually know some examples of these things that we take advantage of in a very practical sense. So in the U.S. Army, they have these special bags, kind of cool things, within a bag. And imagine here that we have food sealed in a plastic bag in here, so don't think that the food is just floating around here. It's sealed, hopefully, tightly sealed here. Melt seal. I'm sure you guys all know what I'm talking about with that. So you have the food in there, whatever it is. And then you put in a bunch of chemicals like magnesium and sodium chloride and a little bit of iron into this. So it's surrounding in there, and it's a solid. Keep that in mind. It's a solid solution. Not solution. It's just solid magnesium, sodium chloride, and iron. And then you might have in here a plastic vial that's filled with water. And then what you do is when the guy is ready to eat this, rather than having to fire up a stove, which might take a lot of energy, he instead, or she, would crack open this tube that's hanging out inside of this outer bag here. Oh, we have to go to class? Oh, we do. Okay. Bye. Okay, so I'm back from class now. And so I break this water tube, and by the way, this is a little confusing, so I should probably get rid of this. Let's just say that we have magnesium in here. You could have had any of those things, but let's just say it's solid magnesium hanging out in here. And the beauty of this is that this reaction, when it takes place, when you combine solid magnesium and some water to produce, oh, wow, that was jumping all over the place, magnesium hydroxide and hydrogen gas, it also produces a ton of heat. So, in some sense, in fact, I should make this happen so that it's a little more clear. Let me go ahead and select up this whole reaction and shift it over here a little bit. Because heat is produced, we can think of heat as being a product. So that's just what I've done there. And that heat will warm up the food, and therefore when he rips open the whole pouch of food, it actually is nice and warm for the soldier to eat. Pretty cool, huh? Now, let's take a look at just the opposite. Imagine we have a situation where instead of this being the case with the exothermic reaction, we have an endothermic reaction. And I'm just going to pause so I can make this drawing. Okay, so in this case, take a look at these vectors. Don't forget that the vector over on the left side, the one that I'm highlighting in red here, right, that is the bond breaking, and the one that I'm going to be highlighting in blue is the bond making, right? So I have more bond breaking than I have bond making. More bond breaking than bond making. And so if that's the case, right, I'm going to have more energy input and less energy output. Right? You can see that that's happening. So that means it's going to take energy into the system. So with the exothermic reaction, we have a reaction that absorbs heat from the surroundings, so it's going to feel totally cold to your touch when you go to touch this thing. Wrap your hands around it. Okay? All right, so what is an example of that? Let's take a look. Okay, in this case, I have a bag inside of a bag again, but I have solid ammonium nitrate in this inner bag, and that's actually not a bag so much of it's probably a plastic tube again. And surrounding this, I have liquid water. So that then in this case, when you go to crack open this situation, it's going to do just the opposite of what we saw moments ago. Now we're going to take the NH4NO3, which is a solid, right? And when you actually make it into an aqueous solution, it sucks heat from the surrounding. So now we have heat as a reactant to create the NH4 plus and the NO3, and those are, oops, I don't know why I just did that. Oh, stop, hold on, let me erase that. Phew, that's better. Okay, so the process of that dissolving is going to create an endothermic situation where all the heat that's surrounding this area is actually going to go into the bag. And what a handy thing to have, say, if you're one of our athletic trainers and somebody gets a bruise on their head and you're out in the field and you need to cool off the swelling as quickly as possible. You take out this pack, crack it open, put it on their head, and you have an instant ice pack. Nifty, huh? Okay, so the last thing I want to talk about is the concept of enthalpy. And enthalpy is symbolized by the capital H. And I want you to think of enthalpy as simply being the energy associated with a chemical reaction. And it's the energy of the substance. It's all the kinetic and the potential energy of the particles that exist in matter. All right? So if you think of enthalpy as simply being energy, that's totally fine. But understand that the reality is there also is a factor that takes into account pressure and volume. But the factor is so small so that the difference between energy and enthalpy is really so small that it really doesn't make a difference to you guys. But what's really more important for us is that if we're looking at enthalpy as being energy, we really want to take a look at the change in the enthalpy that exists from reactants to products in a chemical reaction, right? So delta means change. Okay, so whenever you see a triangle like that, know that I'm really saying change. So we're looking at the enthalpy change in a reaction. And we measure this with a unit called a joule, which is symbolized with the capital J. But really, the joule is not too useful because it becomes such a big number. So we simply use the kilojoule, and 1,000 joules is 1 kilojoule. So if we're looking at this in terms of our exothermic and endothermic reactions, in an exothermic reaction, overall, we actually have a delta H that is a negative number. That may seem counterintuitive, but don't forget that what this really means is that you're losing heat to the environment. So it's a loss, and that's why it's okay to see, I hope for you, a negative number there. And that for an endothermic reaction, didn't really leave enough room here. Hold on. All right, there we go. I just organized it a little better. So for an endothermic reaction, you can see I had the exact opposite, where it's a positive number. And again, that should make sense to you because overall, the chemical system, the reaction that you're looking at here, absorbs energy from the surroundings, and therefore it becomes a net positive energy situation. All right, this was a pretty long screencast. I'm going to stop right now and give you some time to make sure that you've fully comprehended what's going on. Goodbye.